Hello folks, this is video tutorial 10 and I will be doing an explicit dynamics calculation to do a very simple drop test problem. It is this L-shaped region that is being dropped with a given initial velocity on the ground, and the ground is modeled as an analytical surface. This particular tutorial was done in its entirety by the reference that's shown below. However, using the Abacus CAE, so I'm replicating his steps in order to show you the interface and the changes in the interface that the 3D Experience has in doing this problem. Keep in mind that the native FEA solver for the Abacus for the 3D Experience is actually the Abacus program. The dimensions are given here. I'm assuming that the material, L-shaped material, has an elastic plastic uh, response. It can go actually into the plastic mode with this data that you see here. And uh, also, the reference that I showed you includes a, a mass damping coefficient of 25 hertz. And what unit of uh, coefficient of damping, structural damping in vibration is actually it's the variable a, and the units of it is per second, so it is actually hertz. Okay, so this is the value that I'm using, the same value that the other YouTuber used, and we move on. uh, I am using the reduced integration eight noted Breck element reduced integration with this kind of a data. And I keep in mind that in that uh, uh, YouTube video, the gentleman at the end comes back and shows you the uh, artificial energy that's generated, and it's substantial. And what he does is goes back here. First of all, I believe it takes the reduced integration out and also uses the a finer mesh, which I'm not going to do, but it is possible. So that's one difference between this tutorial and the other one. Now, when it comes to 3D experience, to the best of my knowledge, these parameters that I set by the other fellow are not under user's control, so they must be default. So I could not use these values that the reference includes in the calculation. So I'm just using the default value, whatever it happens to be. Now keep in mind that you can find about the default values by going to the 3D Experiences documentation, online documentation. The problem is that it essentially sends you the Abacus manual, and uh, uh, that's not very helpful. Okay. Also, in the reference tutorial, YouTube tutorial, the fellow initially does not include gravity. So when this thing hits the ground, it actually bounces off and goes in the other direction indefinitely. However, later on comes back and adds gravity so that it goes up, and then because of gravity returns, hits the ground again, etc. So bounces back and forth between the ground and the maximum height that it reaches. So in my case, I will actually go ahead and include the gravity from the very beginning. Okay, uh, yeah. So from the very beginning, that's a bit of a difference. And the value of the gravity is just standard 9.8 meter per second square. Total duration of zero point 0.1 second. This is the icon for the gravity. This is the icon for the initial velocity in 3D experience. This is the fixation of the reference point associated with this analytical surface. Okay. And one other major difference is that, not the difference, but one other thing that I'm going to do is to make sure that when this thing hits the ground, it establishes a line of contact. So it's not tilted by any means. So that's why, in effect, it goes up and down at without tilting. In the tutorial 11, I have a bit of a complexity add built into this kind of a problem I actually have two pieces. That L-shaped region is not L-shaped anymore. It's something like a cell phone, and there is let's think about it as a lens embedded in it. So it hits the ground at an angle, and then it kind of tilts to the left and the right and things like that. So it's a bit more complicated. But here it just goes up and down because of the nature of the way I have positioned this L-shaped region. Okay, so one more thing, I believe I have a coefficient of friction. Here I have a coefficient of friction of 0.1, uh, I think zero point 0.1, yeah, point 0.1, the same thing that this fellow is using. I forgot to put down the coefficient of friction here, but I will. Okay, let's go ahead and make our part. So this is the assembly. First thing, I'm going to insert the L shape, right click, insert a 3D part. Okay, this first one is my L-shaped region. So I'm not going to rename it, just leave it the way it is. Let's make it. All right. So I am in generative shape design. Now remember, generative shape design is when you want to make uh, surfaces and wireframes and things like that. But there's also this tab here which allows you to do very simple volumes. So I'll do everything in here instead of going back and forth between the uh, uh, generative shape design and part design. I will stick in here. Okay, so let's go ahead and do this. Let me first draw something that resembles what I have. We'll put the dimensions in a minute. Okay, so this is the inverted L, and then put dimensions here. So this one is 35 millimeters. This is 25. Okay, let's put some dimensions here. This is 5, and this thing is 6. All right. Now there are some fillet radii here, so let's go ahead and put a corner here. This is 2 millimeter radius. Let me try it again. There. So that is 2, and the one down below is 3. Just change the number here. 3. Okay, good. Exit. And then, as I said, I'm not going to go to the part design in order to make this volume, so I'm going to do it right here. So I'll do a volume, and we do a volume extrude, and 5 millimeters in each direction. That means a total of 10 millimeters, because I'm going to click on this symmetry, so this is going to be 10 millimeters, 5 to the left, 5 to the right. Okay. All right, now what you see here, by the way, this is the sketch that I can hide if it's bothering me. All right, now I will tilt this thing a little bit, okay, and there are different ways of doing it. For example, I will tilt it by, let's say, by going to the assembly. You can actually rotate that the way you want it, but it's easier for me to go to the assembly and get the manipulate and rotate it about a particular edge. So for example, rotate a particular axis, so rotating about the x-axis just a little bit, okay? Oh, actually, in that tutorial, this guy tilted by exactly 30 degrees, but I'll just do it arbitrarily. So let's go ahead and, uh, what is that? Rotation about x. Yeah, there. As I said in that tutorial, the gentleman has 60-degree tilt, so we'll just leave it the way it is. Okay, good. Back to this part because I want to create the material properties for it. Under Tools, uh, Material Browser, let's make one. Create a material. I'll call this thing L-shaped. It's a drop test. And today is October 28, 2023. Okay, let's go make it. Uh, Let me refresh this right here. L shape, October 28. Apply, close this, apply it to that part. You have to click on the green check mark to get out of that mode, and then double click on here in order to put the properties in there. Okay, so first of all, it's an explicit dynamic problem, so I need a density. Density is I'm going to put it in 2600. Okay, then you need the Young's modulus and Poisson ratio, abacus multiphysics, mechanic, elasticity, elastic. The Young's modulus is 79,000. That's almost aluminum. 79,000 MPa. Poisson ratio 0.33. Okay, good. And then we're going to go to plasticity, metal plasticity, plastic. Okay, and we put our numbers, the data that had there. So that data was 150,000. Sorry, 150 0. So this is the 150 MPa, which is 150,000 Pascal. It's the yield strength of aluminum, for example. And this next one is 250, 0.05. And then the next data point is 350 MPa, yield strength, plastic strain of 0.15. And finally, 500 MPa, plastic strain of 0.75. Okay. All right, that takes care of this. And then we need the damping. We have to specify damping. So we go down here, ductile metals, and click on ductile. Well, let me see now. Not damage. Hang in there. Yeah, damping. Okay, right there. So this is mass proportional damping, stiffness proportional damping. Traditionally, this is A, this is B, etc. But we're only doing the mass proportional damping of 25 hertz. Unit of coefficient A is 1 over second, which is essentially hertz, cycles per second. And that's pretty much it as far as the material is going. Okay, so let me save this thing quickly. And then I'm going to insert my second part, which is going to be the ground, basically. So right click, go all the way to the top, assembly design, we're already there. Right click, insert 3D part. This is going to be the ground, so I'm going to make it. So on that same XZ plane, vertical plane, maybe YZ plane, sketch. Okay, so I'm going to draw a line here, horizontal line, okay, and that's going to be my ground. So okay, one thing, notice that there is a gap here. So what that means is that you drop it from a height, but there's no reason to do that because if there's no air resistance and things like that, these really can be tangent to each other. So let's see if we can make it tangent to each other so it brings it down. For example, that line control this. Let's see now. This, can I make a tangent to each other? And there are different ways of doing it. This is one way. Horizontal. I don't think that it took it like that. So let's do a few things here. One possibility is this. Another way of doing it is draw a line here, which is as close as we want to that. Okay, something like that, and then turn that into construction. It is construction. Now I say this line control that line. Coincident. The only problem is uh, there may have been some coincidence which won't let you do that. But let's see if I can make it coincidence here. No, cancel. The reason the reason is that when I drew this line, there is a coincidence here, so I have to delete because it won't let this thing go. So you can delete it from here. Let's check it out. Can I delete it from here? Uh, this doesn't let me delete it, so I go to uh, the sketch, which is right here, and under constraints, there is this coincidence that I can delete it from. Cancel that. I can I can delete it from here. Yeah. And now, when I say these two coincidence, let me fix that guy first. Let me fix that fellow first. So this line, I'm going to fix it. Okay, this line is fixed, construction line is fixed, and then this control that. I mean, basically, this is there are easier ways of doing it, but I didn't think about that. These two lines, make it coincident. Control Z. Let me see for a second. Uh, this line, control that line. How about doing some dimension between them, and then say coincident. Okay, good, good. All right. That construction line, if it's bothering you, you can always hide it or delete it, etc. But it really doesn't matter. Now I go to surfaces and extrude this thing in both directions. Let's make it both directions, and yeah, so let me make it a little bit smaller, maybe 10, maybe 15. Oh, 15 millimeters, 15, not meter, millimeters. Yeah, that's better. Let me make sure that this is completely horizontal. So if you go to view, look at the view from different angles. View. So for example, from the front, okay, there's still a little bit of a gap here, okay. I can close that by going and moving that guy a little bit to the construction line, a little bit to the top, but I'll leave it like this. And then there's a side, or right or left. Yeah, you can see that it's completely horizontal. Now, in the tutorial 11, I'm going to come back and in my model, I'm going to make this thing tilted so that it actually hits at a point initially. All right, so let's exit this. We're good. I spent some extra time here, which is unnecessary. All right, now while we are in this part, I create a reference point. I can create a reference point, for example, one of these vertices or somewhere up there. Why don't I do this somewhere up here? Okay, so we are in the essential under point. For example, we can, uh, how about point and direction? Do we have a point and direction? Yeah, I think we do. Or maybe on a, let me see for a second. Why don't I input the coordinates actually? So this is x of x of 0. Y is this way. So let's go ahead. For example, if I make my y coordinate on this side, so we can fix this thing actually, and z of 0. Okay, so let me give a z of maybe 10 millimeter. Okay, and for y, I'm just going to use this. Oh, the other way. The location of it is totally irrelevant. That's the reference point associated with the with the surface, analytical ridge surface. And because analytical ridge surface does not have any material associated with it, so we are good. So now we're going to go to let's go to our mesh module, which is a structural model creation. That's for creating meshes and things like that. MTFEM. All right. Okay, all parts are going to be participating. There's only two parts here, but they're all going to be participating in this model. All right, and now we're going to do meshing of this object. Okay, so you mesh, and we're going to use the sweep mesh. So we select this. Notice that when we do that, the surface, the surfaces that are selected for sweep, these are not what I want. So I'm going to say, okay, let me do that myself. All right. Uh, this one is okay, but this one is not. So I'm going to remove that, and I'm going to select this face. So it's going to be sweeping between these two faces, which is fine. And the size, I believe the size that I'm taking is 1.25, 8 layers. Okay, so I'm going to make this thing 1.25 and 8 layers. Okay, mesh it. There we are. We say okay. Now, when it comes to analytical rigid surface, because it doesn't have a mesh, uh, well, obviously we're not going to mesh it, but there is something that we have to do. We have to declare it as analytical rigid surface. So you go to the abstraction tab right here. See the abstraction tab? You select on it, so click on it, and then there is not rigid surface, analytical rigid surface. You select it. There's the surface. The reference point is that point. Okay, and we say okay. Good. That's pretty much it. So save everything. All right. So now we're going to go to because you're doing explicit dynamics, you can't go to structural scenario creation. You have to go to mechanical scenario creation. You click on it. All right. We are doing a structural problem, and the mesh we created is right there. Select it, that mesh. Okay, so first of all, let's fix that analytical surface. So we go to procedure right there. See that? No procedures exist. So you go to the procedures tab. Explicit dynamics is down here. You select it. Total time is 0.1. All right, and that's good. Now we go to the boundary conditions. How about all degrees of freedom constraint here, which is the same as clamped. It's just that when you do fixed displacement, the icons come out to be looking better. With the clamp, it's just going to be big yellow ball. Okay, so that's all fixed. We say okay. We give, how about giving this thing a downward displacement? So we go to initial conditions, initial velocity, this piece, which is our, you can do it from here or you can select it from the tree. Let me see, you should say part body, not the face. Cancel that. Let me go ahead and select it from the tree. Part body from the tree. Right there, the whole thing. Okay? And in the direction Z, -1, actually, I think in that reference, the initial velocity was minus 0.1. That's 10 centimeter. 0.1, yeah, 0.1 of a meter is 10 centimeters. Okay. I can't remember what the initial velocity was here, and unfortunately I forgot to list it, but I'll make it minus, and let me see, I think it was minus zero point 0.1, yeah, uh, meters per second, underscore second. Okay, minus zero point 0.1, that is, zero point 0.1 is, yeah, I think that's what the fellow is using, and that's the icon for it. Okay. Now we're going to apply gravity too. So under load, there is the gravity here. You click on it and you will select the part body again, right there, and minus 9.81 meter per second squared, or 9,881 millimeter per second squared, which is exactly what I had before. In the downward direction, that's what this minus sign is. And there we are, right there. Okay. Now, the only thing is that uh, let's make sure that this is applied on the rigid surface. I'm pretty sure it is. This restraint that we applied here. Let's see now. Boundary conditions, fixed displacement. Okay, this is problematic. Okay, so what we should do is not that vertex. We should have applied it on the rigid surface. So let me hide that. Let me delete this. For that, I select let me see if I can select the rigid surface. Yeah, there. Not the vertex, not that point, but the analytical rigid surface. That's a big difference right there. Okay. All right. And say okay. One other thing is that notice that the properties is missing here. When I mesh that with the sweep option, I did not specify the properties. So obviously, if you run it, it's going to come back and say this doesn't have a property. So let me double click on this property so that it puts me back into structural model creation. Here is the solid mesh, and you select the, uh, well, doesn't matter. You can select it from here, or the entire part. Okay. Now the problem is that if I do this, it says that I don't know your material. Look. If I click on that, it says I don't know your material. But if I put it on the part body, it's okay because I put the material on the part body. So let me remove this and go and select the part body, which is from the tree. That's just less work right there. It puts on the part body. All right. So back to scenarios. The only thing I'm going to do is for data. So if you go to, let's do a quick save here. We do a quick save. We did it. So we go to simulate. This is where you request data. Click on it. So I want stress, strain, displacement, force, contact, doesn't matter. Every, let's make it every 100 intervals. Okay. That's for the field data. All right. Say okay. Actually, let me cancel that because there is already some default stuff here. So let me go ahead and find out what my default data is right there. Output 1, output 2. Double click on output 1. It gives you all these things by default. Uh, that's because I already set it in the previous run in a different problem. So let me make this thing 100. This is for the field data. And then if you do it on the other one, now notice that it knows these because in my previous run that I made with a different problem, I had used it. It keeps that in mind. Energy every 200, that's fine. So basically, I didn't do anything special because these were already requested. All right, so let's go ahead and run it. Mode and scenario, model check. I don't anticipate any problem. Obviously, if we had not applied that solid section on it, it will come back and say there is no section on it. We have to go back and fix it. But I got it before I actually am running this. As I pointed out in the reference that I'm using, the guy came back after looking at the data, the results generated, said that, oh, it looks like there is a issue, there may be issue with our hourglass control and things like that. This is why he went back and made some changes in the type of element and the size of the element. In fact, he didn't even run it, okay? He looked at only the plot of energy, artificial energy versus time, and said that this is substantial portion of, say, substantial portion of kinetic energy or all energy, and that's why I'm not going to even show you the stresses. Remember, in these tutorials, I am not uh, discussing the validity of the results that I'm generating because I'm using some data from others. And I'm not doing any mesh conversion study. There is no guarantee that what we are doing actually is accurate as far as discretization is concerned. So just keep that in mind. All right, finally, we're going to simulate it here. I did the model check, scenario check, and then simulate it. And this is going to be very quick. Incidentally, if I change the element size and changed it to non-reduced integration, it will take maybe this particular run may take about 20 minutes, okay? But with this, it's very fast. Hopefully, we're going to get to see the ball, this thing hitting the ground and then bouncing back and forth, etc. If not, we're going to have to change our duration uh, slightly, make it longer. Because I noticed that there was a bit of a gap there, and that bit of a gap, nothing happened. It's just that the L-shaped region is going to come down and hit the analytical surface, so we don't gain anything. But anyway, let's see. See, it's going very fast. But of course, there is no guarantee that things are correct because the issue of artificial energy and because of the issue of the, other things that are critical in such calculations. 13%, 14%, yeah. Now keep in mind that some of these are when the L-shaped region is in the air just moving. Okay, those are totally kind of useless as far as we are concerned. There is no drag there to reduce to slow it down. There is no oh, I forgot to do the friction. That's okay. It's all right. I'm gonna finish this thing and go and oh wow, I completely forgot to do the interaction. This is gonna go through that. Oh, this is nonsense. Cancel that. Let me show you. Let me show you what happened. Stop this. I forgot to do the interaction. In other words, that L-shaped region should see the ground. So we say okay. We stopped it, right? So let's see. This is all garbage because this L-shaped region is going to go through the analytical ridge surface. But let's see if we can actually see it. So go to the uh, we stopped at true, but we can still see the result up to this point. Results, which is all nonsense, of course. So let's see. You see? Okay, so let's go and cancel that. Okay, back to scenario. Back to scenario. Okay, So you click on interaction. First, define a friction coefficient. So contact property. This is my contact property. And I think, as I pointed out, the fellow takes this thing to be friction coefficient, takes it to be 0.1 if I'm not mistaken. So I'll use the same thing, 0.1. If not, if it's something else, just put the right value there. All right, good, 0.1. And then we do general contact with the thing that I put in, my contact property, okay? And it will figure it out by itself. I was missing that. That's why this guy went through it. Okay. So pretty much it. Save. Now run. Let's do a quick simulation check, model check, simulation check, and that's good. Simulation check. Okay. This is not running yet. It's just checking for any obvious errors. That is pretty much done. Simulation check out. You can see that. And now we're going to run it. If I if you see that this is taking long too, I'm going to stop the run and look at the results up to that point. I can tell you that based on what the reference is indicating, this mesh is too coarse, and he you know makes a finer mesh. And why he did that is plots the data uh, can, uh, for artificial energy as a function of time, for example, and total energy versus a function of time, and a substantial portion of that. Artificial energy is substantial value. Okay, so all right, now it's the run. You can fast forward if you want until we look at the results, or I stop. Our total time was 0.1. So let's see now. Yeah, this is the total time here. We should go to 0.1. 10 of these will do it. Oh, 100 of those. Yeah. But it's very fast. Let me also click on that plot tab, show you what happens. There's something that I want to mention about this later on when we go further down. So, by the look of it, this took about 1 minute, going to 0.01. So we have to go 10 times more, about 5 minutes. So what I'm going to do is I'm going to stop the recording and come to the end. Okay? Once it finishes, then I'll record again. I'm going to stop this. Stop the recording. Okay, I started the recording again. It took about 6-7 minutes for this thing to complete, and here's the wall clock. You can see that. This is the wall clock, and it's about 412 seconds. to do point one. And if you look at the plots, these bumps that you see here are something to do with how many times it has to do with when it hits the ground. But anyway, so we are fine. Let me close this. We still have our results here. So first of all, a couple of things, and when you look at that reference video tutorial, the fellow says that, okay, I'm not going to even bother looking at the result. Let me plot the artificial energy and kinetic and total energy and see how they compare. So here, let's go to the plots tab. I'll plot this stuff. I'll plot these stresses and things like that later on. But let me go to the plots tab, and there is the history. Where is that? Plot, yeah, XY plots on history data. You click on it, and it says, what do you want to plot? Well, I want to plot artificial energy, okay, and say okay, and I want to do another plot. Notice that this is plotted already here, artificial energy. You click on, again, XY plots on history. This time I want to do total energy. For example, uh, total energy balance, or total strain energy, total energy, total strain energy, for example. And if I check this box, it'll get rid of the other plot, but I want the other plot to be there too, so I'm not going to check this box. Say okay. You see, essentially the artificial energy is high compared to the other thing. You can plot other stuff too, but that's why the guy argues that, well, I'm not going to even bother showing you the stresses and the deformation and things like that, because I know there's a problem, and I agree with that. But let's not worry about that, because we can always go back and change, make this smaller, etc. But let's see now. This is the initial thing before it hits. As you go further down, it hits the uh, it hits this, not yet, because this value is very small. You can see that, but none of these numbers are reliable anymore, because we know that this is, I mean, obviously there's a lot of artificial energy here. So anyway, so what happens is that this is the last one. So let's animate it, see what happens. Let's go back, animate. This is what happens. Okay. Everything is unreliable. And notice that this does not tilt sideways, because I made sure that there was a line contact. You know, this comes directly and hits it at that line in between. Obviously, you can do other stuff. You can do displacement. It's not a big deal. I mean, obviously, this comes down. But all right. So the key is this. This is good-looking colors, but not reliable, because your artificial energy is too high. So you have to go and choose a finer mesh, etc., and then look at the results. So I'm not going to do that. I'm going to stop the video here, and uh, good luck, and you're on your own. And then in the video tutorial 11, I'm going to come back and do a more complicated version of this, so that there is, think about it as being another piece being there which is going to fall off, etc. All right, good luck.